Welcome to Drone Systems and Control course. This is a lecture 22 where we talk about scenario generation for UAV operations. Till today we've been talking about modeling, and then we talked about how do we represent them in 6 degree of freedom equations of motions and simulate. Then we moved on to what kind of sensors required for internal as well as external to look at the context, internal look at the states of the system. Some of the states are not measurable, so we talked about how we can use filters to get the states. Then we moved on to control. Control to bring the system stability, right? We talked about classical approaches. We talked about state space representation of the same system. How do we linearize the system and build a flight controller? Then we moved on to autopilot, where we talked about automatic control systems where we can help the drone to follow specified trajectory, either using PID or using full state feedback. Now we are coming into a very important part where we want the UAV to do specific operations, right? But what this lecture focus on? This lecture focus on scenario generation, right? What kind of technology used for generating such scenarios? How are going to apply autonomous vehicles in such scenarios, right? So it's like machine in the loop or software in the loop, hardware in the loop, how the workflow works. See, very important, we are talking about real-time applications. The control law or the path planning, whatever we have executed, it should work very well, right? The time critical functions. For example, when I talk about a trajectory, I want to go to one position to another position, right? Let's say 0, 0 to 10, 0, which means I want to travel 10 meters in a straight line in XY plane. But how fast I can reach there, right? The time to reach 0, 0 to 10, 10 matters a lot. It depends on physical limitation of the vehicle. It's not the same for every system, right? If you are asking a drone to pitch forward to gain the forward velocity and you are pitching a very high angle, there is a likelihood of wind related uncertainty leading instability and falling, right? So we need to figure out what is acceleration limit, right? What kind of acceleration is possible for the drone to take care of it. At the same time, it depends on what payload you are carrying, what kind of wind uncertainty that you could have. So we have to verify everything. And how do we do it in software? First of all, you have generated an algorithm which can provide obstacle avoidance. Can that algorithm run in real time? That's a question, right? First, we need to check from the software in the loop perspective. Second, we need to look at it hardware in the loop perspective. And then we have to see whether the human interference have to come into picture. How these workflows will happen, right? We may not be covering every aspect of software in the loop or hardware in the loop in the course, but it's very important to know when you are designing the algorithm, their limitation, their effects on the final mission performances, right? We'll also touch base on how we can use the flight controller, commonly used flight controller, the PX4, what we call, which takes care of the basic stability and safety operations at this point of time, brain for the drone. How do we simulate it with Simulink? That's very important, because at the end of the day, control is going to happen in the flight controller, right? So we need to simulate so that software in the loop we can verify. We'll also talk about hardware in the loop with the scenario generation. Hardware here could be a drone kept at an altitude bench. Drone doesn't have to fly, right? I can simulate the scenario and I can model the rest of the equations of motions in MATLAB, and MATLAB can generate the flight control, and that flight controller goes to PX4, and PX4 will just send out the command to the motors, and the motors just going to spin accordingly and generate the thrust, right? We can evaluate the entire workflow and verify whether the algorithm what we have developed, is it sufficient to have real-time performance, right? Now, I'm just giving a scenario. Let's say you have a drone which is flying through urban space, right? And you want to do package delivery as a mission. Think about it, right? When you talk about package delivery, the drone has to fly at a certain height. Here if you see, there is a drone which is flying through the building. Moment you are flying through between the building, not through, between the building, you could have urban canyon flow can come into picture, because at the junction you could have flow. That flow could affect the drone too, right? There is a possibility that there could be a wire, power line, any of this crossing here. How the drone is going to behave, right? How it's going to respond to. Imagine if it's a junction and another drone is going to fly from this side, right? How it's going to handle that? These are the factors we need to look at it. Now let's say I'm looking at another mission for a civil applications, right? So where I want to do topographic map. I have a LiDAR pointing out. I want to generate a map of the whole terrain. How do I get the topography? Right? So I need to first verify in a simulated world, because the challenge here is the height of the terrain is not going to be the constant. Right? If you are using pitot tube, it measures the pressure with respect to mean sea level. If you are using a LiDAR to measure your height, it is going to follow the terrain height. What height you want to maintain? Right? Based on the applications, you have to decide what sensor I want to do, what is the height I want to maintain. Think about it, if a drone have to go for servicing firefighting, the drone enters into the building and you are putting an control, trajectory tracking control, X, Y, Z to be tracked. Suddenly I enter into the building, my LiDAR says your height is only 2 meters, but height of that particular floor is second floor building, let's assume 10 meter is 3 meter is one floor. We are looking at the 4th floor, but suddenly the drone started climbing up, you will have a problem. So what we meant height is, right, it's very important when you are talking about a terrain or a mission. So you need to create that scenario and you need to check whether your global path planning algorithm or a local path planning algorithm is able to provide necessary control, and the inner loop which we talked about, the flight control, is able to make sure the drone is stable following the command. Suddenly you are expecting the drone to turn to 90 degree, right? The rate at which it is turning to left or right is going to be a bigger challenge. How much acceleration I can have? Right? What is the saturation limit? All this we need to verify before we really deploy. So scenario generation is a very important module to understand how the system going to handle various real world challenges effectively. Here the context based sensors going to make a lot of priority, right? Your LiDAR, your camera, your radar is going to play an important role to understand the context or the scenario in which the drone is being present. For that scenario, you need to have a technology algorithm which can generate necessary trajectory such that the flight control algorithm, whatever we discussed in the previous module, can follow those trajectory without compromising the stability, right, and safety. So that's what is very important. This scenario generation is not unknown to autonomous systems. Many self-driving cars uses such kind of a scenario generator, right? It's not just only there, we need to get more data. How do you get more data? So we have to create a scenario and we have to let the drone to fly and get the simulation data. But then again there is a gap from simulation to real. How do you bridge those gaps? These are all future research topics I'm just providing here, but it may not be relevant for the course perspective, but it's very important those who want to pursue further courses and do research in that domain, right? So scenario generation plays an important role in verification of your technology that you are building or algorithm that you are developing. Right? Now, if I want to classify this scenario, it could be static scenario or predefined routes or conditions, right? Navigation through the city, which means I talk about these are the roads, these are the buildings present in the city. Each building heights are going to be 10 meters, something going to be 12 meters, something is going to be 15 meters. So I'm defining all of that. It's a static. It's not going to change in a shorter period of time. There is a possibility new building can come up, right? The time period is long. So those are called static scenarios. Dynamic scenarios, real-time factors like traffic, right? Flow of multiple drones comes into picture. Suppose after this course and you specialize further and you want to use it for urban traffic management kind of an application. When the multiple drones are flying through the city, right? How am I going to handle the conflict? Right? Multiple people can deliver the package. It's a typical problem, right? In any self-driving cars or any cars in the roads, right? How we are going to handle such kind of traffic? Some could be rule-based, some could be sensor-based, some could be reactive, right? Those are dynamic scenarios. Whether suddenly some place become dark, right? Lights are not there. Or suddenly weather develops in that particular location, start raining. How is your context sensors going to work, right? So we need to really evaluate these dynamic conditions too when you are talking about autonomous drones. And there are edge cases, right? Very rare, unexpected events which could happen, and it's it's an emergency scenarios, right? Or extreme weather scenarios. How are you going to handle it, right? It's for example, suddenly road is flooded, right? In air, if I have to say suddenly the wind is very high, I'm airborne, I'm taking off from one location to deliver a package to another location is 30 kilometers away. Suddenly wind picks up, heavy wind, gusty wind, right? If it happens, what shall I do, right? Those are also important when you are developing the techniques, right? So for example, you can do many of such scenarios in MATLAB. So I'm just trying to create one such situation. You see it's a city, typical city where the drone is trying to fly. I have enabled the sensors, playing it back for your understanding. It's a sunny weather. Suddenly it started raining, right? When it starts raining, what will you do? The sun shadows start coming in. Your sensor not able to see, right? Your LiDAR is trying to get the informations. How are you going to fuse these informations to navigate in the typical city traffic with the illumination change, with the condition change? It could be rain, it could be snow, it could be storm, it could be wind also. You can inject all that and then see how a typical drone behave, right? So we need such kind of scenario to be built. Okay. Now, just give you an overview, right? Any application we talk about where we are going to use the drone, multiple domain expertise comes into picture. When I talk about agriculture use case, right, where expert decides how much pesticide or fungicide I have to spray on a plant based on the age of the plant, based on the diseases that I observe, right? Now it's very important to get that kind of a flow rate or penetration below the foliages. The drone need to fly at a different height. If it fly closer, the downwash can damage the plant. So the domain expertise also comes into picture, not single domain, multiple domain expertise comes into picture. The second problem is the complexity of the algorithm. How fast you can detect, how accurately you can detect, that's going to play another important role, right? Then you need to look at technical depth and system stability. Whatever happens, I don't want the drone to fall down and create a damage. So I need to analyze from the stability perspective and ability of the system to perform that particular mission expected by different domain, and the algorithm which is generating the navigation, can I follow the input, right, follow the trajectory, and still I am stable and reliable. We need to analyze everything from end to end point of view. That's very important, right? I'm trying to give integrated workflow. What we saw is overview, right? Now let's see for a typical application how the integrated workflow for developing UAV application comes into picture, right? I have a drone, we modeled it, 6 degree of freedom equations, we modeled the sensors too. Once we have all of this, we also talked about flight control architecture, right? That's where we talk about system architecture. We talked about how the safety aspect comes into picture, flight management module, how the outer loop, inner loops, right, attitude control, all velocity control. We discussed all of this, right? We have those. We talked about external sensors, which basically a perception module. We talked about sensor modules, right? Very important now workflow what we are going to discuss in module 5 and 6 is more on planning and decision control. We have to analyze the data. Based on that, we have to generate a trajectory that need to be implemented in hardware, basically a flight control hardware. Again, we talked about two different architecture when we talk about flight control architecture. One is for stability part to take care. The other one is for perception planning part to take care of it, which can just receive the camera information or LiDAR information, radar information, right? NVIDIA Jetson, or it could be any other system on chip module you can use, right? Now, how we are going to deploy them in this hardware? When we deploy them, how fast this algorithm going to run in this hardware to generate results. Let's say I am talking about 32 frames per second, right, a camera. But my algorithm, let's say I am implementing an AI module to detect an obstacle. I am not able to get more than 5 frames per second. Then how am I going to generate a trajectory, right, and follow? So these are the questions we really need to look at it, right? But then to make this validation, I need a scenario. I can go ahead with a simple cuboid kind of a module, or I can use Gazebo, or I can use Unreal Engine to create a kind of a realistic scenario where these drones are going to fly, where I am going to get this data and simulated data so that I can verify my flow and validate. And finally, how am I going to connect this data to actual physical system, right? Physical system is, I have to send the data to ground station also. Am I able to communicate the data to ground station? How I can control my motor propeller, right, system, that's the propulsion system to generate the thrust. This is very important, right? Now, to analyze all of this, I need some building blocks, right? The building block is whenever we talk about an application, there is a mission for an application, right? The mission need to be planned, right? What is that mission? Let's say I am talking about a package delivery in a city environment. A package need to be picked up from a location A and delivered to location B, right? That's a mission. Now I have to generate a trajectory to go from location which is represented in latitude, longitude, right, to another latitude, longitude. I am just depicting here, right, point A to point B. How am I going to travel? Then for that, what kind of scenario in which I will be flying? Is it going to be a plain terrain, no building, no tree, or am I expecting something? I need that scenario simulation to be done, right? I also need a ground control station which receives the data, telemetry data from the drone and show the position and velocity of the drone or even the battery status in real time for me to validate, right? That's planning part. Very important part, another important part, design and simulate. First thing is, for a given drone, I need to design a flight control architecture to make sure that it is stable, it follows the input command accurately, right? And then you have to have a system logic based on what scenario, what level of autonomy that you wanted to have for the drone, what kind of control loops needed for that. You have to define everything. That's your key component. The brain of the drone is a flight controller. And then you have to have a plant model. The plant model should be as close as possible to the realistic model. We talked about it, how we can represent them accurately, how we can represent the sensors and everything, right? And then you need to have a simulated waypoints. That's where, how do I generate the waypoints? Either I use a star or Digistar or RRT. How am I going to generate these points where the drones have to go through so that they can complete the mission of interest to us, right? When I put this waypoint, I have to really visualize how it will be going through in a scenario. That is also needed, right? In the process of visualization, I could have an uncertainty because I am looking for a context here. Suddenly it becomes dark, my camera is not going to see anything. There is no light. How are you going to respond to when you have situations where the data is not coming properly from the system, sensors, right? Then finally you need to deploy everything onto a hardware, right? And you have to check how your autonomous algorithms really performing. So hardware in the loop validation you need to do. How your Pixhawk is responding to, how your Jetson is processing the data coming from your camera or LiDAR and get your decision control system, and that decision control system is passed on to your flight controller, basically a trajectory, and how you are using the trajectory and how the inner loop, that Pixhawk, follows the trajectory as accurately as possible. This is also important, right? Validate, and finally you need to deploy this algorithm. So if you look at the basic building blocks are plan your mission, design and simulate and develop your algorithms and everything. Once you develop your algorithm, you need to deploy and validate by doing hardware in the loop simulation, right? So what do we need? So if you talk about all the software in loop, hardware in loop workflow, you need input. The input is going to come from your ground control station, right? Basically that is a key factor. A ground control station will define your mission, right? Here is the mission. Let's say you want to spray on a specific agriculture land, right, 2 acre of land. Then the ground control station will define these are the boundary region of that particular agriculture plot. This is your speed limit. This is your height limit, right? All that input comes. Using that input, you pass on all the information to a flight control architecture, right? The flight management system will just take care of and validate all the process and evaluate the model in the loop, right? Basically you have mathematics 6 degree of freedom model. In the 6 degree of freedom model, using the input, I'll validate whether I'll be able to do that particular mission or not, right? And then you have the plant model is also present, right? And output of the plant model will go to your hardware in the loop part, right? Basically your Pixhawk. The states of the system, you have sensor models also here, right? whatever the sensor model, and I have to pass on that to my Pixhawk, where I do a state estimation using the estimated state. I do the control calculation. Finally, I'll just tell you what is the RPM I need from all, let's say if it's a quadcopter, it's all four motors, or if it's 6 or 8, depends on, I have to give all the RPM and thrust requirement, torque and thrust requirement, and again that need to be converted, right? Now you also need a software in the loop where you just validate everything, convert all these model into an exe file, and then you pass on to that and just check whether I'm able to run it in real time, right? This workflow is very important to validate the deployability of the algorithms what we are building in this particular course, right? Your flight control, law, or even the navigation algorithm, whatever you are going to study later, we need to know how can we deploy them in real time. Will they work in real time? Is there any problem when you are combining all the systems together, right? So there are some factors you need to take care of it. How the simulator communicate with the hardware, that particular interface, right, needed between the system. And data, when I am sending it out from my computer, the data received by the hardware, the data rate should match. There should be a proper handshake, right? You need to verify that. And simulator communicates back to the PC. How my system is going to communicate, my controller has to communicate, I want this much thrust, I want this much torque, right? That information have to go back into my PC, where my model can emulate that, right? So these two connections are very important, right? If you look at hardware in the loop, you can deploy directly in PX4, right? You can have the inputs. You can simulate your plant model and flight control architecture. You can have the entire model of your flight controller, and you can evaluate these performance in the software in the loop. Once you are happy, you can directly deploy the flight control architecture, the model in the loop what we have, into your hardware directly, right? So you can have PX4 emulate, instead of model in the loop, I can deploy the PX4 back here. What we will do, we will disable the sensors, because the hardware has a special connections for sensors, and from that particular sensor it will read the data. I have to disable, because I am not going to connect GPS, I am not going to connect IMU, I am not going to connect altimeters, right? But those data are important for PX4 to run. I am going to disable them, right? I am going to run it in a pseudo real time, because all that data whatever required from sensor is going to come from my plant, okay? And if I want to do full hardware in the loop, I can deploy the plant also in a smaller hardware, right? I can validate real-time simulation and testing is possible, where you can just think about how your communication take place between actuators and sensors and different peripherals that you have, and you can validate in real time. If you are not doing that, you can still think about connection that you could have from Pixhawk to your plant model, right? So we talked about hardware in the loop deployment characteristics, right? One of the important factor is visualization. Visualization of flight behavior in a virtual scenario. So we talked about the input coming for a mission. I am defining it my ground control system. The ground control system transfer the mission to your flight controller. That is basically a model in the loop. It takes that data and prepare necessary inputs needed, and the output of the flight controller is going to be your torque and thrust requirement, and that goes on to your plant model. The plant model takes care of it, generate and simulate the 6 degree of freedom model, and then your sensor model picks up necessary output of those acceleration required, or rates. Gyro will just tell me what is angular rates. All that data comes out, and that I am passing on to my hardware, which is a soft data, right? Soft sensor, and my Pixhawk simulating it, I am verifying it and bringing it back. But this loop does not give me how actually this is behaving in real life. So I need a scenario simulator. I have to build a scenario, and in that scenario, how this drone is behaving. Is it going because of the sensor error, because of the trajectory tracking error? Is it going closer to the building or not? I can verify all of this by bringing scenario generator. You can generate your own scenario, or you can use scenarios using Unreal kind of setup, verify them, right? That will help you to visualize your performance, assess in qualitative sense, right? Now, we talked about Pixhawk in detail, flight control system architecture in detail in the previous module. Pixhawk is very commonly used open source flight control hardware. I have taken this for the discussion in the course. One can use any other architecture also, but they need to understand what are we connecting, right? So here we talk about open source, so I thought I'll just pick up this. Pixhawk has a power management board which provide necessary powers for the real-time system, right? And it has onboard sensor interfaces is available. There is one USB for telemetry link. Through the telemetry link, I can transfer the data, the states of the system in real time to my ground control system, right? I can use accelerometers. I can connect the transmitter basically and human taking direct control. Instead of taking the decision making system, he can use a direct control from a transmitter and directly connect with the system and interface with. You can have a GPS module connected, which will give you the global coordinate systems, right? Your latitude, longitude, and I can fuse that information from my inertial navigation system and get my state. So what are the onboard sensors are there? You have accelerometer gyro, you have a magnetometer, you have a barometer. We talked about all of this in our second module, right? And there are different interfaces available. We need to understand these interfaces such that we can simulate the hardware as close as possible. If you want to learn more about this open source architecture, you can go to this particular link, right? It will give you understanding of the open source architecture. Just for a reference or completeness, I'm just bringing in here so that you can appreciate how this is being connected, right? You can read more about it from here. Now there are support packages available in MATLAB. I'm just connecting you here to just understand. MATLAB Simulink as a block library, which basically talks about PX4 sensor blocks. You can bring the PX4 sensor blocks and you can choose what you want, right? You can just talk about battery block. You can talk about GPS block, gyroscope block, vehicle attitude, how you can compute. The radio control transmitter block is there. Magnetometer is there. You can pick what you want. And then you have a PX4 communication module which talks about how your message can be transferred between the system. It has the complete messaging interfaces required, middleware which is connecting the sensor to that. So you can use this particular block library to simulate your hardware as close as possible. MATLAB also provide additional support packages for relationship to PX4 architecture, right? You can have communication interfaces. You can have the parameter interfaces which you wanted to load in the beginning, right? You can pick what sensor you wanted to put Then if you look at the architecture itself, what kind of external connectivity that I can have through Mavlink, right? It talks about how the message from external interface, the data goes into the real-time system, and then you have the corresponding drivers of those sensors. You can talk about all those drivers as being already built in the package. How your remote control, radio link control connects to your flight control architecture, how input can be provided, and that's available here. And the radio link just pass on to your sensor hub, right, and actuator hub, and then all that information goes into your flight control architecture. We talked about these 4 blocks in detail in the module 4. We talked about how attitude and rate controllers has been implemented, how the position control has been implemented, and then how you can bring in the state machine, which is basically a system architecture, take care of the whole interface. The output of the flight control architecture sent as a PWM output, and that will interface with your actual motor control. Okay, more detail about how these interface, and you want to understand how the what are the drivers available. You want to read more about it. You can go to mathworks.com help. There is a support package, and in that PX4 you have more information about integration aspects of these systems. Okay. Now once I have all of this, I can deploy the flight control algorithm to PX4, right? And then I can verify how the position tracking is available. Here it's for a typical X configuration quadcopter. The link will be available to you. You can just follow the link, right, to understand how to deploy this directly into PX4. Okay, basically it provides a complete connections, interfaces, simulating the model in the loop, simulating the plant, and finally deploying the control architecture once you are happy directly into PX4. And once you deploy, you can just simulate that and see whether you are tracking the system accurately or not. You'll be able to see the drone here. I can span a quadcopter in X configuration. I can just do it not necessarily X configuration. You can do it for any configuration also. It not necessarily a quadcopter, you can make it hexacopter. In that case, you have to bring in that particular model into this visualization aspect of it, right? Let's just focus on model in the loop aspect of it. I'm abstracting out from the previous slide where we talked about ground control system. Instead, I'm going to say there is an input. The input basically tells me the waypoints that I need to follow. Basically that waypoint I can take it up and just say this is my trajectory. Given the trajectory, what kind of control loops I need, velocity tracking or position tracking I need to include here, and then plant model, a specific data rate comes from the sensor back to the flight control architecture. I just verify this aspect alone. This is very important for our course. When we talk about obstacle avoidance, global planning or local planner, we only talk about those are all input, and that will generate a trajectory, and that trajectory is given as an input here to the model. Can the model follow the input accurately or not, right? If you see till now, till module 4, we talked about plant and control, right? This is taken care. This particular plant receives the trajectory. Can it follow the trajectory? Okay. Now, when I do that, I want to visualize, right? I want to visualize whether the drone follows the specific trajectory given by me or not, right? I can say now I want to go to a specific altitude, right? Is the drone is capable of going to a specific altitude? Is the drone is capable of performing a circular mission, right? These are the questions that I wanted to understand the performance characteristics of it in a 3-dimensional plane, right? how the drone responds to, so I can assess quantitatively tracking error and see whether the tracking error is acceptable for me or not. Basically, this validates your entire physical constraints present in the system, like actuator limits and everything can be verified to see whether you will be able to track the specific trajectory or not. Right? Now, I can simulate saying that, okay, your takeoff, go to a specific altitude, let's say 2 meters height. That's my command. I can see how the quadcopter takes off and go to the 2 meter height to visualize it. Now, if you want to inject an uncertainty to the plant, you can say, while climbing to a 2 meter altitude, I am going to insert a wind uncertainty. How robust my flight controller with respect to that kind of wind uncertainty, I can verify here. Right? That's very important for us to look at it. We'll be sharing this particular video, right, later in the folder where you can visualize it. Okay. Now, I can look at the software in the loop simulation in that perspective, right. I model the flight controller, I create a exe file and directly connect here and check. Right, the plant output goes here to the host PC. I can verify and simulated things, I can pass it back and I can continue software in the loop testing. Right. Now, we can combine the software in the loop as well as PX4 to visualize again to see how my responses are for a specific input. Right. So, why I am just focusing on these before we move on to guidance control, guidance algorithms, right, navigation and guidance part of it. See, one need to understand we can provide specific global path planning algorithm or decision control algorithms, but how this global path planning or decision control algorithm is going to behave when you are asking a physical system to perform, right? Whether my hardware, the control architecture hardware, or my physical system is able to follow the command required for a particular mission in real time. That validation is very important before we deploy it in a physical world, right? So, we can verify most of these technological limitations of real-time characteristics of the algorithms, whether the interfaces are proper, the visualization will tell you is satisfactory, because it's a subjective phenomena, right? The trajectory error, let's say trajectory error of 0.5 meter, maximum error. Now the question to be answered is it acceptable for a specific mission? Let's say you are passing through a constrained environment, cluttered environment, and already your positional error itself is plus or minus 2 meters, and this 0.5 meter error on tracking means you may be on top of the building, right, then between the building. So we need to figure out where that trajectory error is, for what kind of mission it is acceptable, for what mission it's not acceptable. In that case, which one to override, right? I may have to have a collision sensors on the 4 sides and the collision sensor overrides the positional error, right? So we need to figure it out which one takes a priority and how this local planner comes into picture, which doesn't take the global position into picture because of the uncertainty being there, right? So we have to look at it, right? So for those purpose, the software in the loop, hardware in the loop helps to validate the efficacy of the algorithms or implementability of the algorithms and their performance in near real times kind of a scenario, right? I'll stop today's lecture here. where we talk about what foundational building blocks required for decision control and path planning aspects of it, and how the mission need to be defined, how you need to design the algorithm and implement it, and how you can use the MATLAB toolboxes, PX4 toolboxes to simulate the flight control, right? And how you can verify in model in the loop, right? As this overview I have presented, right? Even though the model in the loop, software in the loop is not part of the course, I felt it's very important for a student to understand the how this is going to influence a specific algorithm that you are building, the algorithm performance in real time, and how it's going to affect the performance of the actual system for a specific applications, right? So in the next class we'll discuss a little more detail into how to use this UAV toolboxes, right, to scenario generation aspect of it. Okay, some of the links will be posted in our course folder from where you can download and read more about it. Thank you.